Thank you, Paul, and thank you, Matt, for the invitation to come to this meeting and give a talk, and thank you, Paul, for that wonderful introduction. I also, before I start, I want to express my gratitude because I've been a faculty member for many years, and having the privilege of working with hundreds of students on this task that I'm going to be describing has been deeply rewarding. Today, I'm going to introduce AguaClara Reach, which is the organization that I'm working for, and provide some context for how it is that we work. And then I'll provide a high-level view of the reason that so many towns and cities and villages don't have access to safe water, and certainly don't have access to safe water on tap. And then I'll give a ballpark estimate of how many drinking water treatment plants are needed on the planet, and then explain how the magnitude of that problem that we're attempting to solve requires us to rethink how we do design, and how Onshape really provides just a new opportunity for us to completely change how we do design and do it in a way that allows us to generate designs quickly, reliably, and to customize them really fast. So this is an idea that I've been playing with of an unbroken design algorithm, and indeed, Paul has kind of set the framework for that, of this idea of parametric design, and then maybe even going beyond that. So AguaClara Reach is an organization, it's a nonprofit, and we have lots of volunteers and supporters who are helping us do what we do. We are kind of the center of this ecosystem from our perspective. We're the center. We work with university teams that are conducting research in helping us develop better ways to treat drinking water. So we have research going on at those three institutions. We then take that growing set of knowledge and we use it to create designs in Onshape. And then we transfer technology that we're creating, including those designs, to implementation partners who are working in country, in this case in Honduras and it's in Central America.
Sorry, Monroe,
yes.
we don't see your screen if you think you're sharing.
Thank you, thank you.
Sorry.
I've done this on many occasions. I get too excited, I keep on going. And I think that my worldview is everybody's worldview, and that's not the case. How's that? Is that better?
Success, thanks.
That is, thanks for that, Matt. I thought Monroe was just sort of leading us into it, but thank you for that, Matt.
So let's go back just very, very briefly. So here we are, there's AguaClara Reach, that's our logo. We've got supporters and volunteers. We work with these universities, Ohio State, Cornell, and NGIT. We develop designs. We transfer those designs to partners, a partner in Central America, Agua para el Pueblo. That partner is working in context, in a national context. They work with the water ministry, the government water ministry, with development banks and other funding sources, so that they can then also work with communities to build those water treatment plants that we're designing and help those communities understand how to maintain and operate them. So that's the ecosystem that we're working in, and Onshape plays a key role in this. But let's back up and go like one level bigger. Like, what is this big problem that we're working on? So the planet is working on sustainable development goals. And the goal is between 2015 and 2030 to work on this list of 17 goals. We're focusing on one of them, clean water and sanitation. And that one is by itself a huge goal, but just the big context is there are 17 major goals that various folks are working on. And then within Sustainable Development Goal 6, if you go down to 6.1, that's where we come in with the goal of providing safe and affordable drinking water for everyone. Now, the problem is that the planet, we don't really have a good estimate of how many people don't have access to safe and affordable drinking water. It's somewhere above 3 billion people, which is an incredibly large number, even given the 9 billion that are living on this planet. So a large number of people don't have access to safe drinking water. And then this is just very rough. Perhaps 50% of those people are relying on a surface water source, meaning a stream, a river, a lake, that requires treatment. And so there's a photo of a stream that was the water source for a town in Honduras, and it arrived at their taps untreated. So that's the problem that we're working on. And then perhaps 50% of those people that have surface water sources live in towns and small cities that could be served by a water treatment plant. And that's now getting down to our problem. Perhaps 1 billion people need a water treatment plant and could benefit by using an AguaClara water treatment plant. Another way of looking at this problem is thinking about the sizes of cities and communities from village all the way up to mega cities like Tokyo. So if you look at the black numbers on the bottom, those are the sizes of cities, number of people living in those cities. And let's just look at between cities of 1,000, this is like a small town, and 10,000, a town, there are about 1 billion people living in that size range. Or similarly, between 10,000 and 100,000 cities that are in that size range, there's about 1 billion people living in the cities of that range. And that in turn means that you can estimate that perhaps there's, I don't know, something like 300,000 communities with 1 billion people living in them total, between 1,000 people and 10,000 people living in each of those communities. So the number of communities that need water treatment plants is actually a very large number. And then another piece of this context is that central governments at the large scale, they're doing very well. They're able to provide water treatment plants for the large cities. But when it gets down to cities that are smaller than about 50,000 people, they often begin to run out of steam, and it's because there aren't great technologies available. And that's where AguaClara Reach comes in with our design. And then for smaller communities that you would think of as being on the village scale or the household scale, there are plenty of non-governmental organizations, nonprofit organizations that are working hard at those problems. And that is actually a really, really difficult challenge of providing safe water to those very, very small communities. So what we're doing is we're taking what the governments have done down to cities of perhaps 50,000, and we're extending the range where there are good designs for water treatment plants so that those smaller communities can have safe water. But with this little bit of humility here, that we've not come anywhere close to solving the next challenges of the several billion people who live in towns and villages that are even smaller. So much work to be done in any case. The challenge is daunting. Everyone in these communities that is getting river water or stream water on tap knows they have a water quality problem. River water on tap at the kitchen sink, like I show in that image, is common in small cities and towns. And maybe this is part of the aha for those of us who are, privileged. We have safe water coming out of our taps every day. And so we don't think about this possibility of what is it like to have dirty water coming out of the tap, and how do you run the households? How do you keep your children safe when the water that comes out of your tap is clearly contaminated, both with particles and pathogens, and has these health consequences of a high incidence of diarrhea among children and adults? So nobody wants this dirty water on tap, and it's far more common than what we would imagine. So I'm making wild guesses here, but maybe it's 200,000 towns and cities that need water treatment plants. So there's a need for a lot of drinking water treatment plants. And the traditional approach would be to design one water treatment plant at a time, using multiple tedious steps where you have this broken algorithm where you have to intervene as a human and transfer information from point A to point B to be able to continue with the design. And that process requires literally months of engineering time in order to design one water treatment plant. And what we need, thinking about these 200,000 towns and cities that need water treatment plants, is we need the ability to rapidly and in minutes, not months, create customized drinking water treatment plant designs for towns and cities ranging from 1,000 to 50,000 people. So you see there's all these big goals here that are actually really difficult goals to achieve. The ability to do it fast, the ability to customize and to a high level of customization, and to be able to have designs that work over a wide range of sizes, 1,000 to 50,000 people. In addition, our design approach has to support the right to repair so that communities can repair and maintain their systems. As part of that, we want to use generic rather than proprietary parts. And there's this interesting mix of additive manufacturing that we use, and then the integration of those generic parts. And somehow our design algorithm has to account for all of that. So looking at, this is real. There are water treatment plants being built using our design approach. Here's folks in Honduras pouring the concrete for a foundation for an AguaClara plant. So these are significant civil works because they're going to be providing, this plant is going to be providing water for a town of 6,000 people. And this is all driven ultimately by a design that was created by us. And at the top of the photo here, you can see the Onshape design kind of floating in the air. And that is what these workers are creating the foundation for right now. And it's an interesting mix of additive manufacturing, where here we see workers laying bricks. And I like to think of that as it's the manual version of additive manufacturing. So that's one element of the design that we had to figure out how to handle. And then there's another piece where you see these white pieces of pipe. Those are actually couplings that are embedded in the concrete. Those are generic PVC pipe fittings that you can buy at a good hardware store. So somehow our design has to incorporate that notion as well of generic parts that you can buy at a store. And then this is just showing the structure that goes around this whole plant. In the end, it will be a lovely building, and this building will be wrapping up, or this plant will be wrapping up and be commissioned perhaps in September or October of this year. Okay, so there was this issue of multiple kinds of parts, additive manufacturing versus generic parts that you can buy in a hardware store. And then this other challenge of, we have to be able to scale from 1,000 people to 50,000 people. And the truth is, we'd like to scale from 100 people to 1,000 people, but we don't yet have a technology that works at that smaller scale. But even in the scale where we are working, this requires some very clever engineering, because we're going from the small photo in the bottom, which is a plant of 6 liters per second. It's treating 6 liters of water per second to make it clean and safe to drink. And this plant at the top, which is treating 120 liters of water per second. So there's a difference in size of a factor of 20 between those two plants. And creating designs that scale in an intelligent way, and that you don't have to intervene as a human, but you have everything coded in algorithms to go from that tiny plant to this large plant, will require some good work in Onshape. So now a little bit about our history and our work with design, because we've been thinking about design for a very long time. So we built maybe on what Ford did in a kind of humorous way. So Ford in 1903 said, I will build a car for the great multitudes. We're kind of thinking about water treatment plants for the great multitudes. And this is how we did it. In 2005, we said, we'll design a water treatment plant for one town. And that was a daunting challenge, and we worked on that. And just about a year later, we realized, you know what, this is a really big problem. There are many, many thousands of communities that need drinking water treatment plants. So let's build a jig or a tool that can design customized water treatment plants for the great multitude. And we did it, and it was hard work. And we worked on this for over a decade. And we pulled together all these tools. We used LabVIEW, MathCAD, AutoCAD, and Microsoft Word and had them all integrated. And you could actually access this using the web, and you could get a customized design using a web-based platform that was created by integrating those 4 applications. That was all well and good, but it was extremely difficult to maintain that system. And it would take more than a year to bring a student up to speed to understand how that system worked so that they could begin to make modifications to the design. So it became unwieldy. And in January of 2017, we realized it was time for a new approach. And so we began looking, and students began looking for alternative ways of creating designs. And really, you look at this timeline, it wasn't until July of 2018, so a year and a half later, Ethan Keller came back and recommended that we migrate to Onshape. And during that year and a half, there was a ton of exploration of the other tools that were out there and a realization that none of them hold things together in the way that we needed. And so when we saw what Onshape was doing, we got very excited. So what are these links that we were looking for that Onshape finally helped us connect? If you think about the history of design, before we had computers, we were using paper spreadsheets to do calculations, all the engineering calculations. And then in a separate room, there was a bunch of drafters, mechanical drafters, who were drafting those designs and creating those sketches. And if you think about these 2 rooms, a room of engineers with spreadsheets and a room of drafters with their drawing tables, in between those 2 rooms, there was presumably an engineer or a manager who carried information from one room to the other room. And that's what I'm focusing on now as this broken algorithm that had to be bridged by a human, whereas indeed in those days, everything was done by humans. But that broken gap between the algorithm of the physics and the calculations being separate from drafting continues to this day. So I want to talk about this evolution toward an unbroken algorithm where we don't have that gap. And there's a lot of pieces to this. So the first part is we need to start from constraints for our design, the physics that govern how the design must work, and then turn that into an algorithm that we then use to drive the next steps of the design. And then I'm going down a path that you might not have been expecting. We have to pull our parts from a database. So there must be a database that contains the generic parts that we might be using. And from that database, we can determine what the exact dimensions are of those parts, where we specified which parts we chose based on the physics. We pull the part from the database, then we get the exact parts of that part from the database. And then there's another whole important piece here is that we're going to have many, many parts. They're going to be modular in nature, and there needs to be a hierarchy of those parts to create these complex systems that in our case is a drinking water treatment plant. And finally, this needs to create a bill of materials. And I just realized now, I said finally there, but there's going to be more pieces to this. Eventually, there's going to be an engineering report that's going to be automatically generated as part of this, which is what the Microsoft Word document was used for in our previous design approach. So there's more of this unbroken algorithm to come. And then there's another piece that I know you're thinking about in the Onshape world, and that is simulation. And I didn't make this be a integral part of the chain. And I have not been using simulation in Onshape, so I may need others to help me think about this. But the way I think about simulation is that simulation is how we learn about the physics, and we then incorporate that into our design algorithm. There may be other ways to think about how you integrate simulation as part of this unbroken algorithm. So I'd like to go through an example of this design process. So suppose you want to design a tank that it will take 1,000 seconds to fill, given a flow rate of 1 liter per second. So the first step, so there's my design challenge, a tank that water spends 1,000 seconds in it, and the flow rate is 1 liter per second. The first step is to do the physics. So we grab our calculations and we think about this problem and we realize, oh, volume is equal to flow rate times time. So we take that flow rate, we multiply it times time, and we get 1,000 liters. So this is the part that the engineers classically did sitting in their one room. Okay, so now we know we need a tank that's a cubic meter in volume. And then we take this to the CAD and the drafters sketch this up. And so we could just say, okay, we'll make this be a meter by a meter by a meter, and we're going to make it out of concrete. And so we're going to have walls that are 10 centimeters thick. So here we go. We can create the sketch of the bottom of the tank, and we've got the meter internal dimension and the 0.1 meter for the wall thickness. And we can take it to extrude, and we can both extrude the tanks, the wall tanks, and the walls of the tank, and also extrude the base of the tank so that it has a bottom, the concrete base. And we do that, and it's beautiful, but it was an awful lot of human intervention to make this happen. We can make this one step better, and we can use configurations in Onshape. So we can create these variables, length and height, give them defaults and minimums and maximums. And we can use those variables now to drive the sketch and also the extrudes. And that's beautiful. That's beautiful. But suppose I want to increase the flow rate to 2 liters per second. So I created a design based on 1 liter per second. If I increase the flow rate to 2 liters per second, I need a tank that's 2 cubic meters. And I don't know what numbers to put in for L and H. I need to calculate what those numbers need to be. So I need an algorithm and some constraints to calculate L and H, length and height. And so this is where feature script gets really exciting. So I can create my own feature script, and here it is. It's my tank is the name of this feature, and I'm putting in some kind of constraints, some defaults. I'm going to say that my slab thickness is 10 centimeters, the wall thickness is 15 centimeters, it's got a height of 2 meters, and I have my other constraints of the time it takes to fill this tank is 1,000 seconds, and the flow rate through it is a liter per second, 1.001 meters cubed per second. And then, so those are my inputs, and then I do some physics. So I'm going to say here that I'm going to do some tank physics, okay? And my function for tank physics is down here at the bottom, and in that, I calculate that the volume is equal to the flow rate, Q, times time. And to make things simple, to calculate the length, I'm just going to take the design volume divided by the design height, and I'm going to take the square root of that, which is, I'm assuming that length is equal to width, and I get my length. And then I'm going to pop all of those variables into the context so that we can see them, and we get this. So now, in my Onshape, I've put my tank as my first feature in my feature list. And when I do that, if I look at variables over here on the right, I can see all these variables that I've defined. So the wall thickness, the slab thickness, the flow rate, and the volume. And now I have a little tank, and I'm linking it directly from feature script. And of course, in the sketch and the extrudes, I'm using these variables, L and T, L and H, as my inputs. And so now when I want to change the design of the tank, I just go back and change the flow rate here, and the tank will automatically change in size. So we're slowly working through this chain. We've got our constraints and our physics and our algorithm done in a feature script. And the next thing we're going to think about is, how do we get this part from a database? So we want to use generic parts that we can purchase. And so the way we do that is we have a Google Sheet that has thousands of parts in it. And that's the core or the base of our database. We are able to pull that into feature script. And then in feature script, we can run a query for a specific part. And we can say, for example, I would like a pipe that has an internal diameter that is greater than 10 centimeters. And it'll look in the database for a pipe that meets those specifications and will bring a particular pipe back for us. As a next step, we need to be able to draw these parts. And the way we do that is we have part services that have this make geometry feature that, given the information that's in the database, it draws the part. And so you can see here an example of a whole family of 22.5-degree elbows. These are PVC components that are made using our big component from the database. So those are all of the 22.5-degree elbows that are in our database, and they are created in using this make pipe algorithm. So we've got parts from a database, we've got dimensions from a part, and we would like to have this, we're like to be using this unbroken algorithm. So here is an example feature script where we have my tank. That's where I did the physics calculations of the dimensions of the tank. And then the next two, getting the part from the database and getting the dimensions from that part, are all happening in one feature, which in this case is a civil tank, a tank that's made out of concrete and rebar. And that civil tank is created by pulling information from the database, and it includes pricing information for those parts, and it creates a bill of materials right away. So we see that I've created all these links all the way over to bill of materials for parts. Here is the feature for this tank. It includes how tall is the tank, information about the wall lengths and widths, and which parts of the tank I want to be showing. And in this case, I'm not showing the top. And it pops that part into the part studio, and it comes fully populated with all this information about these parts, including the pricing for each of these sections of wall, and the fact that these corners are columns and not just standard walls. So all that information is there. And this is harking back to, we work with students. This is the approach that we're using with students. So the students that I'm working with at NGIT and OSU write algorithm in feature script. They create these parts, and I'll just take you through this little animation showing the various pieces. So they do coding in feature script to create this entrance tank. They add the tank, and as soon as they do that, they can see a bill of materials. They add additional parts to the tank. In this case, they're missing a hole, so we add the hole to the bottom where those pipes fit in. They show a water surface. They add a scale to the side of the tank, and you can paint it. So that would be an assignment that students work on. And one more piece, and that is this whole thing of this modular hierarchy. So in order to do this, build these systems that are complex and have multiple parts, we need a way to have multiple parts that know how they have to fit together ultimately. So here is a complete design for kind of the hydraulic and environmental processing parts of a water treatment plant. And it's made up of modules. So there's a chemical feed module, there's an entrance tank module, there's a flocculator module, there's a clarifier module, there's a filter module, and all of those have to come together in Onshape. And each of those parts is made up of additional modules. So there's sub pieces for each of those, and it actually goes even deeper than that. So all these modular parts have to be built bit by bit and assembled. And what's interesting is all of them, almost all of them, need to know what the flow rate for this plant is in order for them to know how they have to fit together and what size they need to be. So here is the whole system for a town of 6,000 people. It would treat 24 liters of water per second. And by just changing one parameter in Onshape, I switched from this 24 liters per second design to a 36 liter per second design. So I only had to change the flow rate, and because I've linked the physics and the parts and this hierarchy all together, I can get a brand new design. And is this clear? Like, I, as a human, don't have to do any further intervention. It's all coming together as just changing one input. And here's a 60 liter per second design. And notice, like, the number of clarifier bays has changed, the filter layout has changed, everything has changed as this has gone up. And there are places where pipe sizes have changed. All of that has happened automatically because everything is driven by that unbroken algorithm. Okay. There are currently 24 towns serving with a total of 96,000 people that are getting water from AguaClara water treatment plants. All of these are located in Central America, divided between mostly in Honduras and also mostly in Honduras and also in Nicaragua. And there are all these people who are just so thrilled and proud of the fact that they now have safe water on tap. And Onshape is now playing a key role in helping us take this forward so that even more towns can have safe water. And with that, I'd like to end, and I'm happy to take questions.
Excellent. Well, thank you for that. That was fascinating. I've never seen this in as much detail before. I had an intern I was talking to just last week that asked me, it was a great question, how I stay motivated when things are getting hard. And I quoted your project, among others, as one of the ways I stay motivated because of what is being done with Onshape. And it is just fascinating to see. But let's get to some questions. First question is, and you know, you just showed us some of the stuff, you showed us pictures of stuff being built, but what's the expected lifespan of one of these plants once it's constructed?
Great question, and one that we also don't know how to answer. Our longest plant has been in operation for 15 years. And I recently had the honor of being in Honduras and asking one of the directors of the water board how long it was going to last, and he was unable to come up with an answer. And when I asked what a likely failure mode would be, the only thing he could think of was if politicians took over running the plant. When I asked the plant operator, you know, what would he see as a major thing that would need to be done to this plant? The only thing they came up with is, well, we're going to need to expand the capacity at some point as the town grows. So these are made out of concrete and rebar and bricks. And that part of the structure is going to last for many decades. I think it's at least reasonable to think of in terms of 50 years. And the plastic components, PVC pipe and polycarbonate sheets, also have a very, very long lifetime. That's also comparable to 50 years. And the beautiful thing is, if those parts fail, those parts were bought in a hardware store in country. And the plant operators know how to build those. So the ability to, you have the right to repair. Those plant operators have the right to repair.
Excellent, great answer, and yeah, thank you. You mentioned actually some of your students are well, you've got a lot of students that are working on this project with you. How does teaching them through this project differ from the sort of old-fashioned chalkboards and textbooks?
You know, there are so many ways that it's different, and I think in most design challenges or homework assignments that students have, they're given a very specific design this particular thing or calculate this specific thing. And I think their eyes get wide when they realize that instead of solving one particular problem, you solve a class of problems. So when they realize that, yeah, I told them to design like that entrance tank for a particular flow rate. And then I say, but you realize you could just go and change that input and you get a complete new design and it's all right. It's already done. So that gives enthusiasm to students. And another thing that I've observed is students are not used to thinking about constraints. And as a designer for so many years, I'm always thinking about constraints. And one of the cool things about constraints is that the constraint that governs is a function of the scale of the problem. And if you're going to make a robust design, you have to be thinking about what constraints might show up as being important. And you have to build the algorithm in so that as the flow rate or the scale changes, that the right constraint ends up being used. And that's just logic, right? if for this set of cases, the size of this tank is set by the fact that you're putting a PVC pipe down through the bottom of that tank, and it has to be wide enough for that PVC pipe to fit through. Okay, so that's one design constraint. And then for another set of flow rates, it might be that you're also filtering trash out of that tank, and there needs to be a trash rack there, and that trash rack needs to have a certain width in order to be able to handle the flow. And so at a different range of flow rates, the trash rack design defines the constraints. So having to think about constraints, and even though it's incredibly simple logic, having to think about that is something that I think is new for most students. And yet it's a core piece of any real design is built in that. So I feel like this approach forces students to think about constraints in a way that they weren't used to thinking about constraints in kind of the traditional mode.
Excellent, thank you. I think this is a bit of a follow-on question. So your intent is to design a plant for a fixed number of people, like 6,000. How do you manage the needed variability if the village does grow to 10,000 people?
Yeah, great question. It's designing a plant to be able to be scaled after it's built is a whole other challenge. There are some things that we can do, and things that we're like. When I was in Honduras again last week for the first time in 3.5 years because of the pandemic, and it was just amazing to get back. And I visited the plant that I showed you photos of, and we talked about this specific case of changing how they construct it, so that when we want to add some additional clarifiers later in its life, it's relatively easy to do that. So we are thinking about that, but it's not easy. And in some cases, if you need to significantly change the flow rate, it's going to mean you build another plant along the side and don't just simply add on.
Okay, thanks. A question from Josh here. Curious about the regulatory bodies that you work with. Do they have any concerns or objections, or are you able to automatically generate design docs or analysis documents, whatever else that they want?
Great question. You know, we've been working in Honduras and Nicaragua in Central America, and the regulatory framework there is a world different than what we're used to here in the United States. We have always been in touch with the regulatory folks in Honduras from all the way back in 2006. So they know what we're doing, and they're actually very, very supportive. And they talk about us as the only organization that they know of that's working at designing better water treatment plants in Latin America, which is part of this, this bit of being a little bit lonely. We would love to have other folks to work with, but they are very supportive of what we're doing, and they come visit our plants, and they have not thrown up any regulatory roadblocks for us. Are we able to automatically generate the design docs? We are not yet automatically generating the design documents. We were doing that in our previous design system with LabVIEW and MathCAD and AutoCAD and Microsoft Word all working together. It is now getting high on my list to add that onto what we do in Onshape. Conceptually, it's a no-brainer. All the information is there in our design. We have this map of maps of maps of maps of all the data that go into making this modular system. So all of the parameters are in that map. Now it's a matter of spitting out an engineering document that is automatically filled based on the information that's in those maps. And the truth is that the regulators in Honduras have not yet been asking for that kind of information.
Okay, well, thank you very much, Doctor. This has been great, and it's been a great way to kick off the symposium. Right, we're done.